When working with database transactions, one crucial thing we must do is choosing the appropriate isolation level for our application. Although there's a well-defined standard, each database engine might choose to implement it in a different way, and thus may behave differently in each isolation level. So today we will explore deeply how each level of isolation works in MySQL and Postgres by running some concrete SQL queries. But first, let's talk a bit about its theory. As we've already learned in the previous lecture, a database transaction must satisfy the ACID property, which stands for atomicity, consistency, isolation, and durability. Isolation is one of the 4 properties of a database transaction, where at its highest level, a perfect isolation ensures that all concurrent transactions will not affect each other. There are several ways that a transaction can be interfered by other transactions that run simultaneously with it. This interference will cause something we call read phenomenon. Here are some read phenomena that might occur if a database is running at a lower level of transaction isolation. First, dirty read phenomenon. It happens when a transaction reads data written by other concurrent transaction that has not been committed yet. This is terribly bad, because we don't know if that other transaction will eventually be committed or rolled back, so we might end up using incorrect data in case rollback occurs. The second phenomenon we might encounter is non-repeatable read. When a transaction reads the same record twice and sees different values, because the row has been modified by other transaction that was committed after the first read. Phantom read is a similar phenomenon, but affects queries that search for multiple rows instead of one. In this case, the same query is re-executed, but a different set of rows is returned due to some changes made by other recently committed transactions, such as inserting new rows or deleting existing rows which happen to satisfy the search condition of current transactions query. Another phenomenon that involves the separation of a group of transactions is serialization anomaly. It's when the result of a group of concurrent committed transactions could not be achieved if we try to run them sequentially in any order without overlapping each other. Don't worry if you don't fully understand this phenomena right now. We're going to replicate each and every one of them in MySQL and Postgres in a few minutes. Now, in order to deal with this phenomena, 4 standard isolation levels were defined by the American National Standard Institute, or ANSI. The lowest isolation level is read uncommitted. Transactions in this level can see data written by other uncommitted transactions, thus allowing dirty read phenomenon to happen. The next isolation level is read committed, where transactions can only see data that has been committed by other transactions. Because of this, dirty read is no longer possible. A bit more strict is the repeatable read isolation level. It ensures that the same select query will always return the same result, no matter how many times it is executed, even if some other concurrent transactions have committed new changes that satisfy the query. Finally, the highest isolation level is serializable. Concurrent transactions running in this level are guaranteed to be able to yield the same result as if they are executed sequentially in some order, one after another without overlapping. So basically it means that there exists at least one way to order these concurrent transactions, so that if we run them one by one, the final result will be the same. Alright, now it's time to find the connection between isolation levels and read phenomena. We're gonna run some transactions with different levels of isolation in MySQL and Postgres to figure out which phenomena are possible in each level. Then we will fill that information into this summary chart. Here I have 2 running Docker containers. One is Postgres version 12 and the other is MySQL version 8. Inside the containers, I have also prepared a simple bank database schema with some initial data like what we are working on in previous lectures. So let's connect to MySQL console and access that database. Here we go. Now to get the transaction isolation level of the current session, we can run select transaction isolation. By default, it is repeatable read as we can see here. This level is only applied to this specific MySQL console session. There's also a global isolation level, which is applied to all sessions when they first started. We can get its value by adding global to the previous select query. By default, it is also repeatable read. Now to change the isolation level of current session, we can use this query, set session transaction isolation level. Then the name of the level you want to set. For example, read uncommitted. After this, if we run select transaction isolation again, we will see that it has been changed to read uncommitted. Note that this change will only have effect on all future transactions of this current session, but not on transactions that run on another session of MySQL console. Alright, now in order to demonstrate the interference between two concurrent transactions, I'm going to open another terminal window, put it side by side with this one, and start a new MySQL console inside it. Then let's copy this command to set the isolation level of this session to read uncommitted as well. Then run the select transaction isolation to make sure it's changed successfully. Okay, now both sessions are running at read uncommitted isolation level. We can now start a new transaction. In MySQL, we can either use start transaction statement or simply use begin as an alternative. Okay, two transactions have started. Let's run a simple select from account query in this transaction 1. At the moment, there are 3 accounts with the same balance of $100. Then in transaction 2, let's select the first account with ID 1. Okay, we've got that account with $100 balance. Now let's go back to transaction 1 and run this update statement to subtract $10 from account 1. Query OK. So if we select account 1 in this transaction 1, we will see that the balance has been changed to $90. But what if we run this same select statement in transaction 2? It also sees the modified value of the balance, $90. Note that the transaction 1 is not committed yet, but transaction 2 still sees the change made by transaction 1. So this is a dirty read, and it happens because we are using read uncommitted isolation level. Alright, now let's commit these two transactions and try a higher isolation level. This time, we will set the isolation level to read committed instead. Okay, the isolation of this session has been changed. Let's start a new transaction with begin. Then we do the same thing on the other session. Set the session isolation level to read committed. Check if the level has been updated successfully, and begin a new transaction. Okay, now let's select all records to see the current state of the account table. Account 1's balance is now $90, and the other two accounts both have $100. Just like what we did before, in transaction 2, let's select account with ID 1. Then in transaction 1, we update that account's balance by subtracting $10 from it. Okay, the balance has successfully been changed to $80 in this transaction. Let's see if this change is visible to transaction 2 or not. Now you can see that when we select account 1 in transaction 2, its balance is still the same, $90 as before. This is because we are using read committed isolation level. And since transaction 1 hasn't been committed yet, its written data could not be seen by other transactions. So read committed isolation level prevents dirty read phenomenon. How about non-repeatable and phantom read? In transaction 2, let's run another select from account, where balance is greater than or equal to $90. Then go back to transaction 1 and commit it. Okay, now if we read account 1 again in transaction 2, we can see that the balance has been changed to $80. So the same query that gets account 1 returns a different value. This is non-repeatable read phenomenon. Also, if we rerun the query to get all accounts with balance of at least $90, this time we only get 2 records instead of 3 as before, because the balance of account 1 has decreased to 80 after transaction 1 was committed. The same query was executed, but a different set of rows is returned. One row has disappeared due to other committed transaction. This is called phantom read phenomenon. So now we know that read committed isolation level can only prevent dirty read, but still allows non-repeatable read and phantom read phenomena. Let's commit this transaction and move to a higher level to see what will happen. Now I'm going to set this session's transaction isolation level to repeatable read. Check it again just to be sure. and begin a new transaction. Then let's copy this command and do the same thing for the other session. Alright, now 2 transactions have been started. Let's first select all accounts in this transaction 1. Then select account with ID 1 in transaction 2. Also select all accounts with balance of at least $80. This will be used to verify if the phantom read still occurs or not. Okay, now back to transaction 1 and subtract 10 from its balance. Get all accounts to see their current state in transaction 1. We can see the balance of account 1 has decreased to $70. We know that dirty read has already been stopped at the lower isolation level, read committed, so we don't need to check it in this level. So let's commit this transaction 1. Then move to transaction 2 to see if it can read the new changes made by transaction 1 or not. Now this select query returns the old version of account 1 with $80 in balance. Although transaction 1 has changed it to 70 and was committed successfully. That's because the repeatable read isolation level ensures that all read queries are repeatable, which means it always returns the same result, even if there are changes made by other committed transactions. Having said that, let's rerun the query that selects account with at least $80. As you can see, it still returns the same 3 records as before. So phantom read phenomenon is also prevented in this repeatable read isolation level. That's great. However, I wonder what will happen if we run this update query to change the account 1's balance in this transaction. Will it change the balance to 70, 60, or throw an error? Let's try it. There's no error, so let's run select query to get the updated account 1. Okay, so it is $60, which is the correct value because transaction 1 has already committed the change that modified the balance to $70 before. However, from this transaction 2's point of view, it doesn't make sense because in the last select query, it saw a balance of $80, but after subtracting $10 from the account, now it gets $60. The math doesn't work here because this transaction is still being interfered by concurrent update from other transactions. I don't know why MySQL chooses to implement repeatable read isolation level this way, but it would make more sense to just refuse the change by raising an error in this case to ensure the consistency of the transaction data. Later we will see that's exactly the way Postgres handles this type of concurrent update in this isolation level. For now, let's just roll back this transaction and try to move on the highest isolation level to see if this issue can be prevented or not. Alright, let's set this session's isolation level to serializable. Confirm that it has really changed, and begin the first transaction. Then let's do the same for the other session. Set the isolation level to serializable, check it one more time, and begin the second transaction. Okay, both transactions are started. Now let's select all accounts in transaction 1, and select just account 1 in transaction 2. Next, go back to transaction 1 and subtract $10 more from its balance. This time, interestingly, the update query is blocked. So basically, the select query in transaction 2 is blocking this update query in transaction 1. The reason is, in serializable isolation level, MySQL implicitly converts all plain select query to select for share. And a transaction that holds select for share only allows other transactions to read the rows, but not update or delete them. So with this locking mechanism, the inconsistent data scenario that we've seen before is no longer possible. However, this lock has a timeout duration. So if the second transaction doesn't commit or roll back to release the lock within that duration, we will see a lock wait timeout exceeded error like this. Therefore, in this case, we must retry the first transaction. So when you use serializable isolation level, make sure that you have implemented a transaction retry strategy. Okay, now I'm going to restart this transaction 1, run the select query, then update account 1's balance. But this time, I'm not going to let the lock wait timeout occur. Let's see what happens if transaction 2 also try to update the same account 1's balance. Here we go, a deadlock has occurred. Because now transaction 2 also needs to wait for a lock from transaction 1's select query. So be aware that, besides lock wait timeout, you also need to take care of possible deadlock situation. Now let's try restarting both transactions. Select account 1 in transaction 1. Select account 1 in transaction 2. Update account 1's balance in transaction 1. Then commit transaction 2. As you can see, the lock is released right away, and the account 1's balance has been updated successfully. Alright, so far we have experienced all 4 isolation levels in MySQL and how they help preventing some read phenomena. Now let's see how they work in Postgres. The effect will be quite similar, but there will also be some differences. First, let's start 2 Postgres consoles on these 2 terminal windows. In Postgres, to get the current isolation level, we run show transaction isolation level command. By default, it is read committed, so 1 level lower than the default value in MySQL. The way we change the isolation level is also different. In MySQL, we set the whole session's isolation level before starting the transactions. But in Postgres, we can only set the isolation level within the transaction, and it will only have effect on that one specific transaction. So let's begin the first transaction and run set transaction isolation level read uncommitted. Now, if we show the transaction isolation level, we can see that it has been changed to read uncommitted. Let's do the same thing on the other console. Begin the second transaction. Set the isolation level to read uncommitted. Then show the updated isolation level. Okay, now in transaction 1, let's select all accounts. At the moment, there are 3 accounts with the same balance of $100. In transaction 2, let's select only accounts with ID 1. Then go back to transaction 1 and update its balance. The balance of account 1 has been changed to $90 here. Now we select that account again in transaction 2. It's still $100. That is unexpected because we are using read uncommitted level, so transaction 2 should be able to see uncommitted data of transaction 1, right? Well, in fact, if we look at the documentation of Postgres, we can see that read uncommitted in Postgres behaves exactly the same as read committed. So basically, we can say that Postgres only have 3 isolation levels, and the lowest level is read committed. It makes sense because normally we would never want to use read uncommitted in any circumstances. Okay, so let's go ahead and commit transaction 1 and select account 1 in transaction 2 one more time. Now you see the committed balance, $90 as expected. Alright, let's commit this transaction and move to the next isolation level. I'm going to start the first transaction. Set its isolation level to read committed. Show transaction isolation level to make sure it's been updated. Then do the same thing for the second transaction. Now just like before, let's select all accounts in transaction 1. Then select just account 1 in transaction 2. Beside dirty read phenomenon, we also want to see how it handles phantom read. So let's find all accounts where balance is greater than or equal to $90. At the moment, all 3 records satisfy this search condition. Now let's go back to transaction 1 and subtract $10 from account 1's balance. If we select account 1 in transaction 2, it will still be $90 because transaction 1 is not committed yet. So dirty read is not possible in read committed isolation level. Let's see what happens if we commit transaction 1. This time transaction 2 can see the updated balance of $80. Now if you run the query to search for accounts with at least $90 again, we will only see 2 records instead of 3 as before. The updated account 1's balance no longer satisfies the search condition, so it has disappeared from the result set. So phantom read has occurred in this read committed isolation level. That's the same behavior as in MySQL. Let's commit this transaction and move up 1 level. I'm going to begin the first transaction. Then set its transaction isolation level to repeatable read. Okay, the level has been changed correctly. Let's do the same thing for the second transaction. Begin the transaction. Set isolation level to repeatable read. Check it again. Alright, now let's select all accounts in transaction 1. Then select just account with ID 1 in transaction 2. Also search for the account with balance of at least $80. Now go back to transaction 1 and subtract $10 more from its balance. The balance has been updated to $70 in this transaction. Let's commit it and see what will happen in transaction 2. Now if we select account 1 in transaction 2, it's still $80 as before, although transaction 1 has committed its change. That's because we are using repeatable read isolation level, so the same select query should always return the same result. Non-repeatable read phenomenon cannot happen in this case. Also, if we rerun the query to search for account with at least $80, we will still get the same 3 records as before. So phantom read is also prevented in this isolation level. Now I'm going to try to run this update account balance query to see how it behaves. In MySQL's repeatable read isolation level, we have seen that it allows the balance to be updated to $60. But here in Postgres, we've got an error. Could not serialize access due to concurrent update. I think throwing out an error like this is much better than allowing the balance to be modified, because it avoids a confusing state where the transaction saw subtracting 10 from 80 produces 60. So kudos to Postgres. Until now, we have encountered 3 types of phenomena: dirty read, non-repeatable read, and phantom read. But we haven't run into serialization anomaly yet. So this time, let's see how it's gonna look like. Let's start a new transaction and set its isolation level to repeatable read. Then do the same for the second transaction. Okay, here we have 2 running transactions with repeatable read isolation level. In transaction 1, let's select all accounts record. Now imagine that we have a use case where we want to compute the sum of all account balance, then create a new account with that total balance. So let's run select sum balance from account. It's $270. Then we insert into account table a new record, where owner is sum, balance is 270, and currency is USD. Okay, now if we select all account, we can see the new record in this transaction. However, what if transaction 2 also wants to perform this operation? Since we are using repeatable read isolation level, the select query in transaction 2 will only see the original list of accounts, without the record that transaction 1 has just inserted. Therefore, it will get the same value for the sum of account balance, $270, and thus end up inserting the same record to the accounts table. Okay, now let's commit both transactions to see what will happen. They were both committed successfully, and there are 2 duplicate sum records with the same balance of $270. This is a serialization anomaly. Why? Because if these 2 transactions are run serially one after another, then there's no way we can have 2 records with the same sum of 270 like that. It doesn't matter if transaction 1 or transaction 2 runs first. We should have just one record of $270 and another record of $540. Okay, so that's how serialization anomaly occurs in repeatable read isolation level. Now let's try the highest level, serializable, to see if this anomaly can be stopped or not. I'm going to start a new transaction, then set its isolation level to serializable. Check if it's really changed. Then copy this statement and do the same thing for the second transaction. Now let's select all accounts in transaction 1, calculate the sum of all balances, and insert a new account with a balance equal to this sum. Now as you can see, a new sum record of $80 has been inserted in transaction 1. Let's go to transaction 2 and run the same series of queries. After this select query, we can see that the list of accounts in both transactions are identical. Let's try to commit both of them. The first transaction is committed successfully. However, the second transaction throws an error. Could not serialize access due to read-write dependencies among transactions. And Postgres gives us a hint that the transaction might succeed if we retry it. So this is good. The serializable anomaly is completely prevented. The 2 concurrent transactions no longer create duplicate records like they did before. We can conclude that Postgres uses a dependencies checking mechanism to detect potential read phenomena and stop them by throwing out an error. MySQL, on the other hand, chooses to use locking mechanism to achieve similar results. Let's see how it handles serialization anomaly. Here are two MySQL consoles that we were working on. Let's set this session's transaction isolation level to serializable. Select it to make sure it has been changed. And start the first transaction. Then let's do the same thing in the other session to start the second transaction. Now back to transaction 1. Select all accounts record. Compute the sum of all accounts balance. And insert a new record with that sum into accounts table. Select all accounts again to confirm that the new record is really inserted. And switch to transaction 2 and run the query to select all accounts. As you can see, this query is blocked, and it needs to wait for transaction 1 to release the lock before continue. As soon as we commit transaction 1, the lock is released, and transaction 2 gets the result of its query immediately. Now we can continue running the sum query and insert query in this transaction. And finally commit it. There's no duplicate sum records. So MySQL has also successfully prevented the serialization anomaly with its locking mechanism. Now I want to try different order of queries in these two transactions. First begin transaction 1. Select all accounts record. Select sum of all accounts balance. Then begin transaction 2. Also select all accounts and calculate the sum of all accounts balance. This time both transactions have the same sum of $1,040. Let's insert a new account with this sum in transaction 1. It's blocked because transaction 2 is holding a share lock that prevents other transactions from updating. Now if we try to insert a new sum account in transaction 2, we will get a deadlock because in this case both transactions have to wait for each other. And since transaction 2 failed due to the deadlock, the lock is immediately released, which allows transaction 1 to complete its insert query. So after committing transaction 1, we can see that a new sum account is successfully inserted. The database stays consistent with no serialization anomaly. Now before we finish, let's do a quick summary of the relationship between isolation levels and read phenomena in MySQL and Postgres. In MySQL, the lowest isolation level, read uncommitted, allows all 4 phenomena to occur, while the next level, read committed, only prevents dirty read. The rest 3 phenomena are still possible. The repeatable read level in MySQL stops the first 3 phenomena: dirty read, non-repeatable read, and phantom read. But it still spares serialization anomaly and even some inconsistent concurrent updates. The highest isolation level, serializable, is the most strict. It prevents all 4 phenomena, thanks to the locking mechanism. The isolation levels in Postgres produces quite similar results. However, there are still some major differences. First, the read uncommitted isolation level behaves the same as read committed. And second, Postgres doesn't use locking mechanism as MySQL, but it uses a better dependency detection technique to stop non-repeatable read, inconsistent concurrent update, and serialization anomaly. Also, the default isolation level in Postgres is only read committed, while it is repeatable read in MySQL. The most important thing you should keep in mind when using high isolation level is that there might be some errors, timeout, or even deadlock. Thus, we should carefully implement a retry mechanism for our transactions. Also, each database engine might implement isolation level differently, so make sure that you have read its documentation carefully and tried it on your own first before jumping into coding. I will put the link to the official documentation about isolation level of MySQL and Postgres in the description, in case you want to have a reference. And that's all for today's video. I really hope it's helpful for you. Thanks a lot for watching, and see you in the next lecture.